We'll talk about the part of your code where, once you start executing within that section of your code, if another process started executing in a section of their code that affected what you're doing, you being interrupted would cause a problem. So we're going to call that the critical section of your code, and we're going to offer a solution to it. A very popular solution is using semaphores. So, so just a little background, even though we spoke about this in the past. Multi-programming environment is where multiple processes are running at the same time, sharing the same processor. So for example, you could have your email open on your desk, you could have a web browser up, you could be running a program, and all three of them look like they're running at once. You're sitting there and an email comes in and you go, okay, but your program was still running, and then your web browser updates maybe some baseball scores or something like that. So it gives the illusion to you like all three programs are running, and none of them have finished, they keep running. It's not like the one you started first has to finish before the next one can start. They're all running, but your computer only has one processor. So how is that happening? The operating system is allowing each one of those processes to have a certain amount of time, a couple of milliseconds, to run, then lets the other one run, then lets the one after that run, back and forth. So that's a great enhancement to computers being able to do that. And every computer has resources on it that need to be shared by processes. Examples that are very obvious to us could be like printers and disk drives and databases on the system. So for example, if you had two programs that are trying to print to the same printer, we wouldn't want to have a situation where one program prints its first page and then it runs out of time. The second program runs, prints its first page, then goes back, the operating system goes back to the first program and it prints its second page. If this went on, then a bunch of people would be standing by the printer shuffling papers together. So that wouldn't work out very well. So we'd like to be able to have a program say, okay, for this section of my code, I need exclusive access to the printer. So I'm going to grab exclusive access of the printer, and then when I'm done with it, I'll free it up for the next process to come along needing it. Okay, so these are some examples of what we would call a critical section. Using the printer is the part of your code that uses the printer. That's a critical section. Once that starts running, you shouldn't be interrupted and lose control of the printer. Other examples of a critical section could be something that's not as tangible as a printer. So I'll go over an example of just code. Hopefully this is a simple example. And it's an example where there are two processes going on. One process is transferring money from your savings account to your checking account. So I know the textbook for this class is very expensive. It's actually, some of you said it was over $200 or near $200, but let's just say, for example, you needed to put $100 into your checking account because you just bought the book, and the book cost let's say it costs $100 in this example. So you might go over to the ATM, put your bank card in, type in your PIN. That's part of your transaction. And if you type in the PIN correctly, you logged in, and then you say, I want to transfer money from my savings account to my checking account. You say $100, and you hit enter. And there's going to be a part where the code is going to look something like this. The savings account loses $100, and then your checking account gains $100. And that's part of the transfer, the code that does the transfer. Suppose your bank from time to time comes by and gives all the accounts for all the people 1% interest. And that's a very high interest rate, unless that, if that's happening every quarter, that would be 4% a year. There's nothing like that going on these days. But it would basically take your savings balance and add 1% interest to it. I'm doing that by multiplying it by 1.01, but I'm adding 1% interest to, taking the value of your account and taking 1% of that and adding to it. Then I'm taking your checking account, whatever the value is, adding 1% to it. Okay, so suppose both of these events happened at the same day, at the same time. Remember, these are now two different processes operating on the same bank accounts. So suppose the bank had one processor that everybody's logging into and operating on. So that would be a small bank, obviously. And let's say the interest goes through at 3 a.m. in the morning because they want to do it in such a way that people aren't too disturbed by it. And you happen to do the transfer earlier that day. Okay, so the two events would look like this. Your transfer would have happened first, and then the bank would have come along and gave interest second. So really, the four events would have happened in this order. $100 goes from saving, gets subtracted from savings. $100 gets added to checking. Then whatever was in savings gets 1% added to it. And then whatever was in checking gets 1% added to it. Okay, so for example, if you started off initially with a savings account of $200 and nothing in your checking account, by the time all four lines have completed, after this process has finished and then this process was finished, your final balances would, you'd have savings would have $101 and checking would have $101. And you'd have a grand total of $202. So you'd look at that and go, okay, yeah, that looks about right. When I signed up with the bank, I was supposed to get 1% interest, and that's what I got. Okay. Suppose the interest went to 3 in the morning, the interest process went through at 3 a.m., and you did your transfer, you logged in at 5 in the morning, and did your transfer after it. Okay, so all that means is that these lines of code ran first, and then these lines of code ran second. So you would get the interest on your savings first, then you get the interest on your checking. Then you would lose $100 from savings, and then you'd gain $100 to checking. So once again, if you started with $200 in savings and $100 in, $200 in savings and $0 in checking, by the time these two transactions completed, this one going first and this one going second, your results would be, you'd have $102 in savings and $100 in checking. The reason why you have the $2 in savings is because at the time the interest was given, you had $200 there and $0 here. Okay, so if you compare the two, there's nothing really to get excited about. Either way, you have $102, and you have enough money in your checking account to cover the textbook, so you're okay with either one. It's just a matter of what order the two programs went in. Okay, now suppose you logged into the ATM at exactly 3 a.m. when the interest was running. They were running at almost exactly the same time. And the bank is using the same processor for both of these. So it lets all the programs that are running at that moment run for a little while. This interest one's going to probably be running for an hour or so because it's calculating interest for every bank account. So they'll let it run, and then let other people log in and get their cash or do their banking if they have to, and then it'll pick up when it left off. So let's say this process has been running, and it's getting closer and closer to the point where it's going to handle your accounts. Okay, and right at that moment, lightning strikes. That's when you come in and you do your transfer. So let's say the sequence of events says you're now running, and you do your savings equals savings minus 100. And right at that point, the process says, okay, I'm going to time you out. I'll get back to you and we'll finish up when you left off. We're going to let some other process run. And then the interest comes in and it gets right to the point where it's giving your accounts interest. So then this line runs, and then this line runs, and maybe it gives interest to some other people too, which really doesn't affect you. And then eventually time runs out, and later on you start running again, and you pick up where you left off. So these 4 lines of code, which impact your checking and savings account, could conceivably run in this order. So it could be savings equals savings minus 100, which is your first line. Then your process timed out. Then your savings equals, you get interest compounded to it. Okay, then your checking account gets interest added to it. Then this process finishes, and then we go back and yours picks up where it left off, and you finish down here. So, your savings balance is subtracted $100. Your savings balance is given interest. Your checking account, which has no money in it yet, is given interest. And then your checking account is credited the $100, which came from savings. So once again, if you started with $200 in savings and 0 in checking, you ended up getting interest on the $100 that was in savings at the moment the interest came through. But you didn't get any credit for checking, so you actually lost $1. The customer lost $1. And I don't know if you've taken a database class, this would be considered an inconsistent result with these 2 transactions. These 2 transactions should never produce this result. Those 2 transactions could produce this result and this result. 101 and 101, that's a consistent result. 102 and 100, that's a consistent result. It's just a matter of the batting order that would determine which one it is. But this is an inconsistent result. Something went wrong. So the issue was, once a process starts operating on this section of the code, it really should not be interrupted. So we're going to define this section of code to be a critical section for this program. Okay. So a critical section is basically the section of code that once your process starts executing in that section of the code, if it is interrupted by the operating system, there is the possibility of having inconsistent results. So we need to put a mechanism in place that will have us not have this problem. So one very easy answer is to allow programmers to have something they could put at the top of, anywhere in the Java code or the C++ code that says, don't interrupt me. And then you go writing code, and then another thing that says, okay, you can now interrupt again. That would work great, except what would all of you do if you had the ability to do that? Right? The first line of your code would be, don't interrupt me. And the last line of your code would be, okay, now you can interrupt. So that would mean that once your program got on the processor, if the operating system said, okay, your time quantum is up, you have to be moved, you would be locked onto the processor and you'd stay there until your program ran. If your program ran for an hour, all the other programs running on your computer would be dead for an hour. Okay, so we don't want to do that. We don't want to give programmers the ability to we don't want to give programmers the ability to lock out everybody. But one thing we could do is we could allow particular resources, and like we had in the last example, data fields could be considered resources that other processes might be interested in using. We could allow them to mutually lock each other out. So for example, this was a solution that came up. The solution came up in the 1960s, And the idea was to allow, oh, sorry, I didn't talk about this slide. So an atomic operation is an operation that once it starts, if during that time, while it's processing, if the process's time quantum expires, meaning it has to be moved off of the processor so another program could get on, the operation will be given an additional amount of time to just finish the operation before it gets moved off. So we don't want to allow users that do that because they'll make their whole program an atomic operation. But we will allow, the operating system will provide very, very small, very quick methods or functions that once called will, if during the call of that function, the time quantum ran out, it would be given an extra amount of time just to finish up. So these will be called system methods. So in 1965, the idea that the method would go like this. So someone came along, we'll talk about them in a second, came along and said, why don't we have a method we'll call it try to reduce, and there's a variable attached to it. So the variable's value will be, the variable's value is S, and its value will be the count of how many of the resources that this variable is tied to are available. So let me give a concrete example. Suppose you want to access the printer because you want to print a document. So your program has to say, well, I'd like to print it, but if someone else has access to the printer, your program's going to get stuck, should get stuck, waiting for the printer to become available. So you're going to ask, the question you're asking the operating system is the printer available? If so, I'd like to take it. If it's not available, I guess I have to wait. S is going to represent the value of the printer being available. 1 meaning it's available, 0 meaning it's not available. And the reason why we'll have a 1 being available is we can extend this later if we have identical resources. Like if you had 10 printers, we can set the value of S to 10, and then every time somebody wants a printer, we subtract 1 from it to let us know how many available printers are left. When it finally hits 0, we're going to have to get stuck. So it's a counter of how many of the resources we're trying to access are available. So if there's only 1 resource, we're going to initialize the value to 1, meaning it's available, and then we'll check to see if it's available or not. So if you want to access a resource, you would issue this atomic operation. The atomic operation is supplied by the operating system. If the value is, and this is a system variable, so only the functions supplied by the operating system can read and write and alter them. If the value is 1, meaning the resource is available, well then that's good. That means we got the resource. We set the value to 0, and the resource is ours. If the value is not 1, meaning it's 0, that means somebody beat us to it. Somebody got the printer before we came along and said, can we have the printer? So what does that mean? Well, we have to wait for them to finish. Then we can start printing. So what will the operating system do? Will it allow us to stay on the processor and just keep asking, is it available? Is it available? Is it available? Is it available? And if it's available, then why would it ever become available? If we check if it's available and it's not, and we check again and we check again, it'll never be available. The only way it'll become available would be if the process who has it says, okay, now I'm done with it. So it wouldn't make sense for us to keep processing and asking the same question over and over again. So the way this code will work is we'll say if the value is 1, we'll set it to 0 and it becomes ours. If the value is not 1, and I just wrote out a sentence in English here. I'm going to show some pictures depicting what the operating system does in a second. The operating system is going to move this process that's asking for a resource that's not available. It's going to move it onto a queue of processes that are waiting for this resource. Okay. So when you go to access a resource, you have to issue this atomic function first. And if the resource is available, you'll get it and block anyone coming in for the resource after you. And if it's not available, you'll get queued up waiting for it. When you're done with the resource, you're going to issue a function called increase. And the way this works is, this is your way of saying, okay, I'm now done with the resource. So now, what you're going to do is, if anyone's waiting for it, you can alert them, okay, this thing's now available, it's yours to take. So, if there are processes waiting for this resource, the operating system will assign the resource to that next process and allow it to start running again. And again, I'm going to show you some pictures. If I wrote out the code here, it would look like a lot of data structures code moving pointers around. So I'd rather write it out as English and then draw a picture of what's happening. If nobody's waiting for the resource, so if you're printing a document and there's no other process waiting for it, and now you're done with the printer, you don't need to assign something with the printer, nobody wants it. So just set the value back to 1, and then later on someone else will be able to just come and take it because the value is equal to 1. Okay, so this idea of these two atomic operating system functions, and these were the original proposed names, try to reduce and increase. They were proposed by a famous computer scientist named Dijkstra. And has anybody, you guys seem pretty quiet today, but has this name popped up in computer science, in your classes? Maybe in the banker's algorithm? Is that the, I'm sorry, no, you speak up, it's up. Yeah, shortest path algorithm. Right, so in the shortest path algorithm in your algorithms class, analysis of algorithms, yeah, he gets credit for that one too. But this idea of adding to the operating system these two atomic functions that just pinpoint the resource that you happen to be sharing is what he came up with. So he was asked, he decided for shorthand reasons, because it would take a long time to write, try to reduce and increase. So he's Dutch, and he was asked, eventually what he called those two functions were the function P and the function V, and he was eventually asked, well, where did those letters come from? And I think this was his answer. He said, well, came up with the function try to reduce, and whatever the phrase for try to reduce, oh, here is the phrase. That means try to reduce in Dutch. It starts with a P. So I guess this is maybe someone Dutch can help out. Maybe the reduce and increase start with the word V, so that to somehow separate them. But anyway, the phrase try to reduce in Dutch starts with the letter P, and the word increase starts with the letter V. So those became the names of those functions, the P and V function. So what I mean by that is now we can just call this the V function, and we can call this the P function going forward. P is a lot quicker to write than try to reduce. So that'll help us out. Okay, so what happens? What happens in the code, the try to reduce or the increase or the V function? What is going on inside that code? And instead of writing the code, I wrote out a sentence saying what it does, but now I'm going to pictorially show you what the P function does. The function now P of X, we're going to call the variable X, meaning the X resource. Okay, so in our operating system, we have a ready queue. And the ready queue points to process control blocks, which are blocks of data about your process. It's not the actual code of your process, but it's data about your process. Like what resources does it currently hold and what its priorities are and information like that. that'll be in the operating system. But this is going to be, the ready queue is going to be a linked list where the end of the list points to the beginning. So it's not really a queue, it's a loop, a linked loop. So basically, in this picture, what we're saying right now is the ready queue process, this is the process control block for A. A is ready to run, meaning it's not waiting for any resources. If you put it on the processor, it would start running. Process B is ready to run, which is the next one after A. After B comes C, after C comes D, after D runs, it would go back to A. So we have 4 programs running on this processor. And A runs for a little while, then B, then C, then D, then A, then B, then C, then D. And right now we have another thing called the running pointer. C happens to be the process that's currently running. We also have a resource X, and we can have many, many resources. And there's a queue. So this is a pointer to all the processes that are currently waiting for resource X. Not one that currently has it, but one who's waiting for it because someone else has it. So right now, whatever this resource X is currently controlled by process A. A asked for it, A did the P of X, and the value of X was set to 1, so set to 0, and A got it, and A proceeded. Now B has run, now C has run. So C, in this example, I'm saying C requests resource X, which is currently held by process A. So, let me go back to, I'm sorry. So this code, this is now the P function. P says if the resource is available, let's take it and proceed. If it's not available, the operating system moves this process to the queue of processes waiting for the resource. So what does that mean? This process is running. This is storage. This is a snapshot of the storage of the operating system. And it just issued the P of X function. The value of the variable X was equal to 0 because A made it 0. So the operating system comes in and says, okay, we got to move some pointers around. And the pointers get moved around to look like this. So the next pointer of C became the running process. The running pointer got updated. D's next field is still A. B, which used to point to C, now points directly to D. And C, which used to be pointed to by B, is now being pointed to by the X queue. So what has happened is, the programs that are now running on the processor are D, which is currently running, and next is going to be A, then B, then D, then A, then B, then D. C is going to now start getting skipped because it's not on the operating system's ready queue. So it's going to be skipped. It's going to be skipped for a while. What's going to get it to not be skipped anymore? One of the programs that is running has to somehow tell this thing to get off this queue and back onto this queue. Otherwise it's going to sit here forever because it's never going to run again. It's just sitting on a queue that never hits the processor. So, at this point, let's see what's going on here. A, B, and D are ready. D is running. And the operating system moves process C to the front of the X queue. So C asked for something that A is currently holding and has not finished executing out of its critical section. Hasn't issued the V command yet. Hasn't given it up. So C is waiting. Now, D runs and also requests the same thing. So now D wants something that C wants but can't get because A has it. So what's going to happen now? What's going to happen now is the operating system will put D on the end of the queue of all processes waiting for this resource. Most likely the queue will also have an end of queue pointer so to make it very easy to put something onto the end of the queue. So now the ready queue, which is really a loop, is running A, then B runs, then A runs, then D runs. It's just going to do this. and C is waiting for resource X, and D is really waiting a lot. It's going to be waiting for A to finish with it, then give it to C, then C to be finished with it, and then C will give it to D. So the state of this right now is C and D are waiting for resource X. Okay, so A and B are now time sharing the processor. What's good is C and D are not spending any time on the processor. There's no point in putting them on there. They need this resource and A is not done with it yet. So we need A to issue that V command to give it up. So C gets back in the ready queue. So at this point, let's see, we were here before. A issues the V command. So let me go way back now. A issues this command. So it goes with respect to resource X. A says, if there are any processes waiting for the resource, the operating system should assign the resource to that process and allow it to return to running again. So what does that mean? Okay, A is running, issues the V atomic operation. What does the atomic operation say? Well, this resource that I'm giving up, resource X, if anyone's waiting for it, which there is somebody waiting for it, the operating system says, does this queue point to something? If it's not 0 and it's pointing to something, someone wants the resource. Give the resource to them, so inside that process control block, we record all the resources that they have access to, so we record that. And then we have to move this block back into this loop. Since this one is the one that's just giving up the resource, I guess we might as well say, well, this has been waiting a while, let's put it next in line. So we'd actually have process A point to this resource, so it'll start running right after A is finished. And then this one will point to B. It makes the data structure work, the updating the pointers easier to just put it right after this one, instead of trying to remember where it was in the batting order from before and try to put it back to its old spot. That would require a lot of storage and not really serve any purpose. So what we're going to do is we're just going to, as the operating system, we're going to put C right after A in the ready queue or ready loop, whichever you want to call it. So when A finishes what Dijkstra calls the V command, the V atomic operation, the operating system will perform these steps right there. So now C is running, and the ready queue processes that if you put them on the processor, they would run without hesitating. It's C is running, then B will run, then A will run, then C will run, then B and A. And D will still be waiting for this resource. D has no idea who has it. All D is doing is waiting for one of these running processes to eventually issue the V atomic operation, which will then pick it off of the queue and put it, the waiting queue, and put it back on the ready queue running. So let's see. So in this case, A, B, and C are ready. D is waiting for resource X. C is currently running. The operating system moves C back onto the ready queue after A. So that's the events that have happened here. Okay. Okay, so and now using this, we can make our lives a little bit easier. They're very easy, it's very easy functions to use. You just put the P function before your critical section starts and your V function after it, and you just count on the operating system to handle everything. So now what we could do is we would say P of X, and then we would do our checking and saving stuff, and then say V of X. And then we'd say P of X, we do our checking and saving stuff, and then say V of X. So one possible schedule would be the one where we say the variable X starts off at 1, meaning the resource is available. We say P of X, so there's no waiting. We get the value of X and we proceed. We update the savings account. Then all of a sudden we time out. And the other process runs, and it issues a P of X. And it's going to have to wait because we haven't done the V of X yet. So it has no choice but to get stuck and can't proceed, which is exactly what we want. So now we eventually get back to running, we update the checking account, and we issue the VFX, which is basically saying that we're done. So now, the savings, the other process, this one, which issued this PFX and got stuck, it got taken off of the ready queue and put onto the X queue, had to wait here until we issued this line. We blocked these lines from running until this ran, and this won't run until we finished all the work we care about in our critical section. So we issue the VFX, and now this thing can proceed. So while this did the PFX, the operating system moved it onto the X queue, and while we did the VFX, the operating system moved it off of the X queue back onto the ready queue, and it just started running. So these lines just started running. And then these 3 lines ran, and we were done. Another way would be if this one ran first, wanted to do the interest, got this thing, then let's say it timed out right after this atomic operation. Then we start running, well, we would get stuck. We would do the PFX and we would get stuck. This thing would update the interest first, and then say, okay, I'm done with it, signaling us to get off of the waiting queue and onto the ready queue, and then we would start processing. Both of these schedules are consistent, and then using these Dijkstra operations, the P and the V, we're guaranteed to have consistent results. Okay, so you might think the mindset started to turn into these variables X get bonded directly to a physical resource, like a printer, or a disk drive, or a bank account. In this case, it's a combination of a checking and a savings account put together is considered a resource that when we operate on it, we want to lock it and unlock it. But by the nature of these functions, we can think of them, we can use these variables to mean really anything we want. We can use these functions to do process scheduling too. So Dijkstra proposed a pretty popular, if you Google producer consumer problem, it'll describe this problem. And the way this problem works is there's 2 processes running, and one of them is producing something and one of them is consuming the thing that's being produced. So let me give just a simple example. Suppose there's a program. A lot of printers these days have like their own memory on them. You could put a huge document on the printer and then you don't have to worry about it, it'll print from its own memory. But older printers used to be, you'd send one page, the computer would send one page to the printer, it would print it, then it would send a message back saying, okay, send page 2 now. And you'd send page 2, and then it would print it, and then it would ask for page 3. So in that model where like the process is producing page 1, and then it's waiting for produces it into a buffer, waits for the printer to print it, and then say, okay, now produce page 2. And then the printer consumes page 2, and then says, okay, now produce page 3. It's kind of that model. So that's the producer-consumer model. And the way we can write the code for it using these P and V functions is to just simply do this. We have a producer process and a consumer process. They run forever, so I'm just doing a while one, which is just a loop that runs forever. And so what we have is while one, we have our code produce, whatever that code is, whatever it's producing, we have our code for consume. And we're doing a P function and using a variable, we're using 2 variables here, P and C, which really aren't tied to a resource. They're used more for scheduling. So we're saying, we're going to say that the P value is set to 1, meaning that is available, and the C for consuming is not available. So the consuming process is not available to run, but the producing process is available to run. So the producing process, if it issues this command, will set the P value to 0 and proceed. if this process happened to have run first, because both of these processes are running at random times. So if this one started running first, it would get stuck right here. And what would it get stuck for? It would get moved over to the ready queue, and what would wake it up? Some other process issuing the V of C. If you do a P of any variable and get stuck, the only thing that's going to save you is some other process doing a V of that same variable. So, that makes sense? So, yeah, so the way this works now is the producer process will definitely run first, then signal this one to run. When this one, the producer process, once it runs, it has actually, even though if it loops around again, it has blocked itself because the variable that was originally 1 was set to 0. The only way to get it set back up to 1 again so this could run for a second time would be if the consumer process finished. So, so now what we can do is we can use this for signaling. So now what's happening is the producer process runs first, then the consumer one runs second, the producer third, the consumer fourth, and we have a schedule going back and forth. So now we can do the same thing with two processes. We could say, what we could do is we could say that the producer runs first, and then here one of the two random consumers runs. Then the producer runs, and then either one of these could run, and so on. And there's other examples like this. I think probably go on for a long time. We can have a situation where we have three separate processes. This process runs first, then we want this one to run second, and this one to run third, and then this one fourth, fifth, sixth, in that order. So we just use three variables. Start the first one off with a 1, next two values of 0. This one is guaranteed to run first. These two would immediately get stuck if they happen to run first. The only way for this one to run would be for the first one to finish is the only way the second one could run. The only way the third one could run would be if the second one finished. And the only way the first one could run for a second time would be after the third one finished. So this guarantees a schedule of this one runs first, then this one runs second, then this one runs third, then the first one runs 4, the fifth one runs 6, the sixth one runs 7. So we can schedule processes using these things. In this case, these variables are not tied directly to a resource. They're used in conjunction with each other for scheduling.